Hello everyone, my name is Ehsan, and in this video I'm gonna present a study about Ensemble classifier for misuse detection using n-gram feature vectors through operating system called traces. This study presents a misuse-based intrusion detection systems over a pretty new and modern system call-based dataset with combining multiple different machine learning approaches. The main techniques they have used are n-gram and number of statistic approach to extract features from a raw data, smooth methodology to balance the imbalanced classes, and majority word ensemble learning for classification. The novelty of this study is although there are many studies reporting high performance for anomaly and misuse intrusion detection systems on several benchmark datasets, the applicability and relevance of these designs are limited due to nearly all benchmark datasets, with the exception of ADFA-LD and ADFA-WD, being out of date as they don't model many of the modern day attacks. ADFA dataset is a dataset that model many of the modern day attacks, although their use was mainly constrained to anomaly detection, with few studies leveraging them for misuse detection, which they aim to address this in this study. They also use multiple machine learning based approaches and present a very promising result, nearly perfect accuracy, which makes their study rich in terms of research work in both fields of cybersecurity and machine learning. Alright, let's take a look at the benchmark. ADFA-LD dataset consists of three parts. Training and validation traces were collected during normal process of the host, ranging from web browsing to LaTeX document preparation. Unix program audit is the generator of traces. The ADM data subset consists of 6 types of common cyber attacks, as you can see in this table. Each one is provided in 10 different files, and each file contains 8 to 20 traces. As I've mentioned, comparing with previous benchmark dataset, ADFA-LD dataset is much more representative of current cyber attacks and is position provide a more convincing and appropriate framework for intrusion detection system development and performance evaluation. As the data for system call traces have only sequence of numbers corresponding to those system calls made by the applications, there is a resemblance to text classification domain. Accordingly, a well-known text pre-processing technique called the n-gram method is employed to generate the feature vectors. As you might know, an n-gram model is a type of probabilistic language model for predicting the next item looking back to the previous n-1 items. The window size of n or system call numbers in this case typically moves one or more than one numbers forward over a sequence of given numbers. In this study, authors employed two different approaches for extracting features and reducing dimensionality of the input patterns, where patterns are n-grams. The most frequent unique features in the form of n-grams from each class are extracted from the raw trace data. Then, to eliminate the effect of noise, most frequent patterns, regardless of uniqueness, are extracted based on the statistical attributes of the appearance frequencies. Also, they employed the count of occurrence of each unique n-gram in the training data, where unique means those n-grams which happens exactly in one class and not the others. Accordingly, higher values of n produce more unique attributes. Both the frequency of occurrence and uniqueness of n-grams are affected as the n value change. In order to account for this effect, the use of all n-grams in the range of 1 to 10 for generating the attributes from the raw call trace data is justified. This hybrid method provides a richer pool of features. Top 250 most frequent n-grams from the normal class and top 100 most frequent one from each attack class were selected for inclusion in the training dataset for classification. The overall pre-processing approach described up to this point has a potential weaknesses, where a number of attributes which could play a pivotal role in the classification might have been eliminated. Some n-grams appears a lot in one class and very few times in other classes are eliminated due to overlap. Therefore, such n-grams are not removed even though they may exist in the training data set of more than one class. Comparison of the distribution of average values for the appearance frequency of attributes shows that there are a number of very frequent attributes that are eliminated from the original training set. It's convincible that these eliminated attributes might constitute or be part of a strong signature of a specific class. There are several attributes whose appearance frequencies have high standard deviation values. Right figure shows that only a small number of these attributes are included in the pre-processed training set following duplicate removal. Almost 98% of attribute occurrence frequencies have a mean value that is lower than 10. The objective is to identify those attributes whose occurrence count mean values are considerably higher than the rest. Hence, top 2% of engrams with the highest standard deviation value in the original training set are selected. Each row of the training table is allocated to one class. In order to find those attributes which occur very frequently for a specific class, they calculate the ratio of the maximum value of the given attribute across all 7 classes to the sum of the occurrence counts of the same attribute for 7 classes. If the ratio value is close to 1, then the associated attribute must have mostly occurred in one class and very few times in other classes. This figure represents the ratio values of all attributes in the original training set. Those attributes with ratio above 90 will be added back to the pre-processed training set, regardless of if they appear in multiple classes. The training set for the classifier mod generation employed the entire TDM and 60% of ADM dataset, while the testing set included the entire VDM and rest of the ADM dataset without any overlap. The ADM dataset is split into 2 subsets of 60% and 40% ratio randomly. For classifier development, the training dataset is further split into 2 data subsets at the ratio of 67% to 33%. The larger data subset is used to generate the classifier model, and a smaller split validation dataset is used to prevent overfit. For the multi-class case, because the number of instances of each type of attack is considerably lower than the normal class instance count, they have equalized the number of instances for each class using the smooth algorithm. Here we can see the classification table and confusion matrix for both multi and binary class problem in validation phase with the provided metric results indicate that the true positive rate for each class is high, while the false positive rate is low, with an overall accuracy rate approximating 96%, which looks very promising for the next step as testing. This table shows the performance result for the multi-class model on the testing dataset. The detection rate for the normal class is nearly 100%, as only 2 out of 4372 normal traces are misclassified as web shell attacks. For any missed detection, it's overwhelmingly an attack trace being misclassified as another attack class, but not as a normal trace. Conversely, only 2 normal traces are misclassified as attack traces that implies the false alarms. On the other hand, this table presents the performance of voting ensemble classifier applied to the binary class problem. Its performance considerably improves compared to that of the multi-class case. All 301 attacks are detected except 2, and there is no false alarm among the total 4372 normal traces, which means all the normal traces have been classified correctly as presented in this table. The confusion matrix also shows that only 2 traces are misclassified as normal out of 311. And here is the conclusion. This study has some advantages like low processing time and very promising for detecting attacks, but it's poorly performed for detecting type of attacks, and it requires large data samples for signature recognition. Thanks for listening.